p-value and
Right.
variance.
So that formula, right. So if you take a look at the, focus. Right? I'm having so the deposit arriving according to a Poisson process. Okay? So a deposit or withdrawal is a Poisson process. With what is that rate? What is that rate? The rate is 5. Of course, the unit of time here is 1 hour. The rate is 5. And here, tell me according to the formula. So I guess what I say is that divided by NT and 15 being the summation of K from 1 to N sub 15 YK is the, so this should be the total cash. Total cash, I guess I want to call cash flow. Total cash flow. In 0 up to 15. And according to the formula that we have from last time, expected value of 15 is simply given by expected value of y1 times expected value of 15, where expected value of y1 is the average cash being withdrawn for each transaction, namely that is 20. So this is 20. I'm pretty straightforward here, and the meaning of this number of the arrivals is simply lambda multiplied t. So that will be lambda is 5 times 15. Pretty straightforward. See. And the variance. So the variance of the total cash up to 15 hours is simply given by what? Expected value of N15 multiplied by variance of the y and plus variance of N15 multiplied by the value of y1 squared. This is, again, this is 5 times 15. The variance here is, did I give you the variance? I do not, but I do give the standard deviation. So that will be standard deviation squared plus the mean squared. So that will be 300 squared plus the mean here is 20 squared. What is the variance of the Poisson distribution? So the mean is the lambda. The variance is still lambda. So the variance of the Poisson distribution is still the rate, which is 5 times 15. So we call it Poisson lambda. Mu is the same as the sequence square. Alright. And second moment of this. Oh, sorry, so I guess this is wrong here. Okay. So this is wrong here. So this is supposed to be 300 square here for that. And this is supposed to be 300 square plus 20 square. Okay. I guess I got that right there. Is that correct?
So it's like this formula. So the last term is it like the expectation of y1 squared, or is like the expectation squared?
Pretty sure it's the expectation square. Not
Oh, got that wrong?
yeah.
Oh, okay, okay. My bad. Let me double check here. Where is it? Oh, so that will be the mean square, not really like the second moment. Yeah. Oh, I see. My bad. Oh, okay, my bad. We got even that wrong in my notes here. Alright, so that will be, so the mean is 20 and square up. Okay. All that is clear now. And, oh, okay. Alright. Just some number. So some number. Alright, so in order to answer the last piece in the question, which is the approximation of the chance the total daily withdrawal is less than that number, because I need the following theorem. So again, let me do it once again, given y a ID independent of a wholesale process. So a NT, a wholesale process. Right. And again, let me denote again the NT to be the summation of the y. So like a 1K from 1 to NT. Then the following is whole, 1. NT as stationary independent increment. To recall, being stationary increment means that I have a distribution of MT minus MS depends on the difference, so T minus S, but not on T and S. It only depends on the difference. And the second piece, it means, and for all any time, say T1 less than T2 less than Tn, I have Tn minus Mt minus 1, all the way down T2 minus T1 and T1 are independent. So that is part 1. Now part 2 is following. Part 2 that the so-called central limit theorem for the MT. So I have MT minus the mean MT over the root of the variance of MT. That is going to standard normal as T going to infinity, and the convergent mode here is in distribution. this go to that in distribution. And this is an advanced property. The advanced property of the compare and cross-sell process. The first part basically coming from the fact that the Poisson process has stationary independent increment, and you have the yk being independent of that entity. That is the first part. But the second part is more advanced, pretty tough to see directly. So we just skip the proof here. So we just take this for granted. So I guess I want to go back to this now. So as a quick consequence of this theorem, we can easily, just a simple approximation for the problem number 1. So we have probability, I guess we have to say much. T less than 6,000, pretty much like approximately, sorry, at 15, approximately like probability of V less than 6,000 minus what? Mean of and 15 divided by the variance of n15, taking the root, where Z is a standalone. Okay.
So, you're assuming that T is big enough so that we can like approximate it with the limit. So 15 is big.
Yeah, 15 is wrong. But of course here, like here this problem is only 15, but I guess that would be, I think that would be, because typically they converge really fast.
Oh.
Yeah, typically. Converge really fast. All right, so just allow me to finish this section of the video and move on to the next one. I guess I believe in the lecture notes I do have the proof of this piece. So maybe just go home and take a look at that. Right, so now section 2.4 on the transformation. First part is about the so-called thing. Okay. So-called thinning procedure. Basically, I'm going to split a Poisson process into sub-processes. To give it a motivating example, to give an example. What does it mean? Thinning. So suppose I have a, let's say, guest, right? Arriving according to a Poisson process. And of course, for each guest, let's say independently, each guest, of course, is either male or female. So each guest independently being either say male some process, let's say n sub t. Right. So let me denote by, let's say n sub male, so m t. All right. To be, this is the number of male guests arriving among the interval from 0 to t, and similarly, n sub f t to be the number of the female guests. All right. So originally, I have a Poisson process modeling the number of guests arriving up to time t, and then let's split that process into two further sub-processes. One is for male, the other one for the ladies. And the fact is that under these assumptions, then the male and female processes are actually independent, and they are indeed Poisson processes themselves. So here, in fact, following from n sub m t and n sub f t are independent Poisson processes. So the remarkable fact here, I would say, is the fact that they are independent of one another, even though they seem to be very related. One process kind of like the complement of the other seems to be so, but in fact they are independent. Pretty counterintuitive here, actually. All right, so that is the following theorem. This is theorem 2.11 in your book. So what is the theorem? So let me formulate the problem here. So it's given, again, given the following. So given a sequence of yk, all right, and b with the same, of course, same mass function. Say probability of y being little j is denoted by pj, of course, all right. Suppose I have this. Okay. And then, of course, also independent and so let's say one can do that, and or independent of a Poisson process n sub t, a Poisson process with the rate lambda, right? Okay. Then we're going to be denote for each little j, we're going to denote n sub jt to be the following. So one indicator function j evaluated at the yk, k from 1 to n sub t, right? You can think about this being the indicator function. Think about like that male female guest over there. Each time is equal. J will count, increasing my count or unit, right? So you think about it this way, say from 0 up to the time t. Okay. So I have the first guest arriving, second guest arriving, say t sub nt. All right. And then each time we're going to consider this. So suppose if y1, b, and j, I'm going to count. Say y2 is not equal to j, I don't count it. You know, y in the middle here, something like the yk, b and j with the y here, and sub t is not equal to j, so I'm going to count that. Alright. Okay. So that is the number of times yk, b, and j of the time t. So this is number of times the event yk, b, and j occurs for k from 1 up to n sub t. Alright? And with the convention, of course, with the convention that if nt is 0, namely they have no guests arriving, then obviously this has to be 0. Summation of k from 1. Sorry. If this is the case, then n sub jt is 0. Okay. Then the theorem says, then, part 1, we have these processes. So n sub jt is a Poisson process with the rate in, what is that? So lambda times t times p sub j. I guess for the sake of completeness. T times probability y, b, and j, which is lambda t p sub j. So that is a Poisson process with that particular rate. You can think of, well, I mean, that should be very intuitive, because this will occur with that probability. And so altogether, on average, suppose if I have, on average, if I have lambda t guests in total, then the number of times these guys will happen with that number of this time. Yeah. But the second part is more remarkable, I would say. So the sequence, njt, now I'm counting on j, right, are actually independent. So independent. So they are independent. Let me maybe walk through a couple of these properties in the argument. So let me mention number 1. So how do I show this is a Poisson process with that rate? So I need to show the following. We need to show 3 pieces. The first one is nj at 0 is identically 0. Second, njt plus s minus njs is a Poisson distribution with the rate lambda and the difference here is T times Pj, and the last piece NJT as independent increment. Right, so we need to establish three pieces in order to confirm it is a strong process. That one there. So maybe let me move it up here. All right, so keep that location. All right. So what else do I need to keep? Alright, so I guess I'll erase this piece. I'll erase this. Okay, so the first piece is clear. This is already clear. Really nothing to say because n sub 0 is 0. So because n sub 0 is automatically 0. Right? So if you have nt being 0, then n sub jt has to be 0, obviously. The first piece is clear, trivial, I would say. Now the third piece is also clear if we accept the theorem from previous section. So to see independent increment, we note that the yk are supposed to be independent of the first cell process n sub t, and as a consequence, the process the random variable is 1 sub j yk, right? Those random variables are also independent of the entity, obviously, because these have nothing to do with the entity. Okay, so as a consequence, let's say by theorem 2, back in the previous section, we have n sub jt being the sum. To think about this as being a compiled Poisson process. Okay, k from 1 to 19 is a compiled Poisson process. I'm sorry, I should say compiled Poisson process. I should say, according to the previous theorem, this process here has independent increment. But I don't know the distribution yet. I don't know the distribution. And I know it needs to have independent increment. Okay, let me call it then for our start step. T1 less than T2 less than T sub n. Sequence n sub j Tn minus n sub j Tn minus 1 all the way down n sub j T2 minus n sub j T1 and then n sub j T1. They are independent. independent. So that previously finishes part 3. So now in order to conclude point 2, I have to do some computation directly on that random variable. So now, C and J T plus S minus and J is and JS is the cost of lambda T is Q. So I have to do the nothing I can do but just directly computing the PMS minus and JS. Right? B and A, what do I call it to B and A? Okay. So I need to compute the mass function directly. And so as usual, I'm going to do the law of probability. So that will be the summation on maybe call it k from 0 to infinity. Probability of this event conditioned on and t plus s minus s k times probability and t plus s minus ss. Okay. Right. This is all for probability, isn't it? And then, to think about it, all right? So this is the time s. This is the time s plus t. Okay. So suppose I tell you among inside of this interval I have k guests in total. I suppose I tell you this information. So that means I have whatever here, right? So I can tell one prime something. What do I want to call this? I want to have okay. The first guess from here. Up to here I have k guests. Writing inside of this the time interval. And so what does this tell you? So among these guests, I have a times j occurs. So I have an a times y being j occurs among k guests. Right? So I'll just say nj t plus s minus s of js being a given nt plus s minus ns being k. This event is basically this. Right. I'm going to consider k guests, right? And if any of them satisfy this event, I'm going to count. So in total, I have an a set time. So I have a time that event occurs among k guests. And so what does that mean? That means I'm looking at, of course, here with probability, of course, with probability p sub j each. Right? So what does it tell me? That tells me I'm looking at a binomial distribution. I'm looking at a binomial distribution. And so So, so, as maybe just this is a binomial with the parameters n, b, and k, and the probability to have it is probability of success is p sub j. So now the sum, I will rewrite the sum. K starting from 0. I have, well, I guess, hold on, I'm guessing something wrong here because it cannot be 0. So if that is 0, this I have A guys here. So that's supposed to be not bad. Not bad. In doing the counting. So that would be A plus K. This is A plus K. That would be better than A plus K, yes. So I have A times occurring among A plus K. Sorry guys. So because I need to make sure the total gas here has to exceed this number A. Because otherwise that doesn't make any sense. So I have A plus K. Alright. And this has to be A plus K. Right? Because otherwise, suppose if I count like from 0, I have no guess, then it's impossible to have A times 1. That is ridiculous. So that's why I have these arrows like this. Alright. So anyway, so now that will give me A plus K. Choose A, right? Maybe you just write in the factorial. So I have A plus K factorial, A factorial, K factorial. I have P of J raised to the power A, 1 minus P of J raised to the power B K. And the probability, this is equal to that. That is the first term, so E minus lambda T times lambda T raised to the power A plus K over A plus K factorial. Recalling, this piece here is the binomial what A plus K J. This is the first sum with the rate momentum, right? And now I just have to combine the stuff. So summation K starting from 0. I will be able to cancel out a couple of stuff. So remember, only K is running. So whatever doesn't depend on K will be pulled out. Remember, only the K is running. So what I can pull out here, I can pull out A factorial. I can pull out Pj raised to the A. This is already canceled with that. I have lambda T raised to the power A, E minus lambda T. Alright, so I am left inside of the sum, being what? 1 over K factorial times 1 minus Pj to K, and lambda T raised to the K. So what is that sum?
Exponential.
It is What is that sum? Taylor expansion. Exponential. Taylor expansion, right? Of the exponential. So this is simply e to the 1 minus p sub j lambda t. Yeah? No? So what is that? So we're calling e to the x, the summation of x to the k over k controlling. Right? So that is that. I have this exponentials, and now the last piece is the cancellation. So what do I have? So are we able to get rid of the e minus lambda t over here? I am left with the other guy. So basically I come down to e to the minus p sub j lambda t times pj lambda t together raised to the power a over a factorial. Right? So that is the Poisson process. So hence, this is the Poisson process, sorry, Poisson distribution with the rate being lambda t times p sub j. Okay. All right, so that is part one. It's about the Poisson process. And now part two, the fact that they are independent. For the sake of simplicity, let me just do for two processes. So now to see independent during the degree of n j t b and a and sub I t b and b. Right? I want to be able to split them up eventually. Then I get the independence for each time t. So how do I split up for it? Well, as usual, so you will have to do that thing again. So but here it's a little bit simpler. This is conditioned on as a t being, okay, I have a plus b and then I need to add k. Alright, probability as a t being a plus b plus k, and this is the summation of k. Alright, as usual, right? And then, okay, so from the previous part, you see if I have one term, that is simply a binomial. Now, if I have two, what is that random variable? So from time 0 to t, right? Suppose I tell you I have in total a plus b plus k trials. So this is one trial, second, up to here. So a plus b plus k trial. Right? Then among these trials, 8 of them I have y mean j occurs. And I have b of them y mean I occurs. So let's say this is y mean j, y mean I, maybe y something else. Right? And so y mean I here, y mean j here. And so I have among a plus b plus k trial, right? A times y being being j curves, and b times y being little I curves. Yeah. With probability, this is probability p sub j. This occurs with probability p sub I. What is that distribution? Trinomial, or in general, multinomial. So that is let me write down. So we got a plus b plus k factorial, a factorial, b factorial, k factorial, p sub j, a times, p sub I, b times, and the rest, p j minus b sub I, k times, trinomial distribution, right? And then you multiply with the nt being a plus b plus k. So that is multiply with e minus t a plus b plus k over k. Right. That's all. Right. Alright, so because I already ran out of time, let me mention real quick that well, I mean, so after simplification, eventually you're going to get the algebra over here. You will get e minus the first guy, so lambda t p sub j. T p sub j raised to the power a over a factorial, and second piece p sub I, t p I to the b over b factorial. Alright, and that will be probability of a sub j being a times probability of a sub I t being b. Right? But it shouldn't be difficult. It shouldn't be. The argument is pretty much the same as this piece right here. Alright. I guess I will just finish this chapter 2 here. We do have some exercise in the lecture notes. Take a look at that. Could be in final exam. And